radiographic contrast media because especially when we are looking at structures that are very similar in composition. So when you look, especially in the abdomen, where you have all these different parts, your spleen, your stomach, your liver, your bowels, large and small, and then your kidneys and ureters, they are all very similar in composition. So we need to use some kind of contrast media to highlight and delineate that structure from the surrounding structures. So we're going to be using iodinated contrast media. So we're not going to talk about barium because we're doing that in the other class. We're going to talk about iodine here in this class, okay? So the main component of injectable contrast media here is iodine. Iodine has the atomic number of what?
53.
53. And what's barium?
56.
All right. So iodine has atomic number of 53, and it does have the ability to pacify different your vessels as well as organs. We say it's radiopaque because it is a positive contrast media. Radiographically, how does it look?
White.
It's white, right? Because it has the ability to absorb X-rays, and it mimics the same characteristics of that of bone.
Mm-hmm.
So it appears white on a radiograph. Okay. Most types of iodinated contrast is water-based or water-soluble, meaning what?
We can absorb it.
Okay, so we absorb it, okay? So it's absorbed by if it's not from vessels, it's absorbed by tissues and organs, which eventually makes its way back into the circulatory system, and then we eventually excrete it through
pee-pee.
Okay, pee-pee. You said pee-pee.
He's
Okay.
practicing. He's practicing for the baby.
Pee-pee.
Oh, that's right. Okay, some procedures may require oil-based or water-insoluble iodinated contrast. The problem with that is that it does persist a little bit longer in the organs, so it's not easily absorbable. In the olden days, they did do procedures using oil-based, especially in myelograms. So let's just say somebody had a myelogram, we use oil-based contrast. 3 or 4 months later, we're doing another myelogram, and the contrast is still there. So it doesn't get absorbed that quickly. Some places they use oil-based contrast for hysterosalpingographies. I don't even think they do silographies anymore. You guys know what silography is?
Mm-mm.
Okay.
Yeah, okay.
Yeah. Oh, were you telling me what it was? Oh. Oh, you're choking. Because you went like this.
Oh, the universal sign for I'm choking?
So this deals.
Yeah.
I was like this. She's smart.
Yeah.
Silography is a study of the salivary glands.
Oh.
So this is most commonly done now. I don't think we do it in radiology anymore, but I mean radiology in the sense that not regular X-rays, but I think it's done in CT. And then here we have myelography. Okay, you guys know what myelography is, right? It's a study of
Spine?
No.
No? Bone marrow?
Nope.
No?
Study of the sheath of the spinal cord. Spinal cord. Yeah. The myelin sheath. The myelin sheath. All right. Water-soluble iodinated contrast, it does have multi-purpose, so in addition to it going to the vessels, it also can be, again, used for organs. All right. Misconception about iodinated contrast is that it's not a dye. Okay, dye usually has some color. The contrast that we deal with is colorless, so it is not a dye, and we try not to say dye, especially in a procedural room, right? We don't want to say dye. So most are colorless and transparent to visible light. Its ability to enhance visualization of structure is due to its ability to absorb X-rays. What's another word for absorption? What do we say? Attenuation. Okay, attenuation. All right, so now we're going to get into the chemistry of the contrast agents that we use. I'm trying to keep it as basic as possible because I'm not a chemist and I don't really know the physiology behind molecules and things like that, so I'm just going to be straight up honest with you. All modern-day iodinated contrast is structured into what is called a tri-iodinated benzoic acid or a 3-salt molecule. So it's a salt molecule, just like Morton salt, right? Iodine has salt. So the salt in the iodine is going to be the main component in producing this opaque image on a radiograph. So the water-based contrast may be supplied in either ionic or non-ionic. So the word that I introduced to you guys earlier was iodinated. Iodinated meaning it has iodine. Okay? Do not confuse that with this next term, which means ionic and non-ionic. What does this refer to?
Oh man, I forgot.
Okay? Ionization, ionic compounds. Okay? Like salt is Na plus, because it has a positive charge, Cl negative, right? Okay? So they're ions. So oftentimes, students have a tendency to get iodinated and ionic confused. So iodinated means iodine. Ionic is referring to the charges of that particular molecule. Okay? So they come in two forms. They're also described as monomer or dimer solutions. Specific characteristics are based on the number of particles per molecule, numbers and types of side chains attached to the basic iodine atom, and use is determined by physician and other considerations. So let me just keep on going here, and then we can talk about this a little bit further. So, are you guys familiar with some of these names here? Have you seen these? Have you guys started your research and finding the different contrasts in your departments? Do some of these sound familiar?
Yes, kind of.
Conray,
Mm-hmm.
hypake, pantopaque, renographin, isobute.
Ooh, optic.
Okay, octarase down here. Okay. All right. I'm going to keep referring back to this chart, okay, because it is a very good chart. But it lists it by their generic name and then their brand name. I'm more familiar with the brand name. I'm not familiar with this at all, because we refer to the contrast by their names. And then we'll talk about the configuration of these molecules and the difference between ionic and non-ionic contrast, and also their osmolality, being high osmolality or low osmolality. So let's go ahead and start talking about those terms. So in order to completely understand iodinated contrast media, it is necessary to understand these terms. Also keep in mind that fluids in the body, both in the bloodstream and surrounding body tissue, is always going to be in a state of equilibrium. Okay? Outside pressure, inside pressure is always going to be in a state of equilibrium. Okay? And if the pressure is stronger on one side, your body's going to automatically make that shift until you equilibrate on both sides. Okay? So the first term here is osmosis. Osmosis is the diffusion of molecules through a semi-permeable membrane from a place of higher concentration to a place of lower concentration until you have equilibrium. Okay? Until you have equilibrium. We all know what osmosis is, right?
That's true.
So we're familiar with this term, but these next two terms you're probably not as familiar with. Next one here is osmolality. Osmolality. Osmolality controls the distribution and movement of water between body compartments. It is the concentration of molecules per weight of water. So what does that mean? Well, a highly osmotic agent, such as radio-opaque contrast, will attract water so that dilutional effects will occur to equilibrate pressures between two semi-permeable membranes. So what happens is, again, this is going back to 153. All right. So here we have, let's just say here we have blood vessel, okay? Here's a blood vessel, and then we have surrounding tissues, organ cells, or what have you. All right? So here we have our blood vessel. Now let's just say, for instance, we injected contrast media, iodinated contrast media. Iodinated contrast media is highly viscous, and it also has molecules and particles that has a tendency to draw and cause interactions from its surrounding spaces, okay? But let's just stick to viscosity for just a moment. contrast is going to be very thick. Okay, so we inject it into the blood vessel. Remember what we said, your body's always going to be in a state of equilibrium, right? So because your vessel now has all this thick viscous material in there, it's going to want to equilibrate. So it's going to start drawing fluids into the vessel until you have equilibrium. And it's in the sudden change and shift of all these different organic parts of the cell and the surrounding tissue, and also the pulling of water from the surrounding spaces is what can cause an anaphylactic reaction. Okay, an anaphylactic reaction and other types of molecular changes. Okay, any questions so far? So, going back to what we're saying here. So radiopaque contrast in the bloodstream will cause fluid from outside the bloodstream to be drawn into the bloodstream until osmotic pressure is equal on both sides. Other intravascular constituents such as albumin, electrolytes, and sugar are being diluted. These are all things that are necessary in metabolism and vital to our life. Along with contrast crossing the blood-brain barrier, adverse reactions can occur. The blood-brain barrier is simply that. It's a barrier between your blood vessels and your brain and your spinal cord. And anytime you introduce radiopaque contrast, such as iodine, you are breaking down the barrier, allowing these other constituents to enter the brain and can cause neurological issues. All right. So do we understand osmolality? Sorta, okay. Oh, good.
Don't
Nobody
ask.
answered yes. Nobody. Everybody understand?
Yes.
All right, good. Okay. Osmolarity is the same as osmolality, but instead of weight, it refers to it as volume. So one refers to weight, the other one refers to volume. Okay, weight versus volume. Okay, do we know the difference between weight and volume? Right? Okay, weight versus volume. Osmolality and osmolarity are often used interchangeably in reference to osmotic activity. However, one measures in weight and the other one is in volume. So let's talk about the three broad categories of iodinated contrast. So there's that term again, high osmolality. High osmolality, ionic radiopaque contrast media. So high osmolality, ionic RCM, it is an ionic compound. Its molecular structure is 3:2, which means you have 3 iodine atoms for each 2 particles of solution, or in this case 2 particles or 2 molecules instead of 2 solutions. It has a monomer configuration, meaning that it's the most simplest model and can be bonded to identical molecules to form a polymer. This is going to be the most chemotoxic to blood and body tissues because it is hyperosmolar, again, very thick, very viscous, so it will have the tendency to pull and steal from the surrounding tissues and organs and cells. Now, remember what we said, iodine is salt. So when we look down here, it says that although the salt molecule is stable when it dissociates, okay, remember it splits up, in a solution such as blood, its atoms, either cation or anion, may cause other dissociations and cause unnatural bonds. Note, it is going to be the anion, okay, of this atom is going to be the anion that gives you opacity. This is what gives you the opacity on a radiograph. It's what contributes to opacity is the anion. Anion?
No.
Anion. All right. Okay. Any questions? So something that's ionic, we've already know ionics is saying that it does have some kind of charge, right? Isn't that what ionization is? Okay, it can be a positive charge, it can be negative charge, but it has excess energy. And so that's what iodine has, is that it is capable of, because it has excess energy, it can cause those molecular changes. Okay? Okay, next one here is low osmolality, non-ionic. So the difference between this one and this one is that instead of 3 to 2, we have 3 iodine atoms for each of the molecules. The osmolality, we're talking about here, is it weight or volume?
Weight.
Okay, talking about the weight of iodine in a solution. The weight of iodine in the solution is reduced because we are removing the number of cations, cations, in the solution. We are removing the number of this stuff here, in the solution.
It's cation.
Okay, cation, okay? So if we are removing more of the ions that can cause these molecular changes and disruptions, it is less toxic to the body. So it causes less chemical reactions. But
It's not as opaque.
it's not going to be as opaque. Okay, any questions? Okay, low osmolality, ionic. It has the same structure and configuration of joint ionic compounds, but it reacts similarly to a non-ionic. In other words, because of the way they were able to bond these molecules, they were able to gain back some of that opacity that they lost under this configuration, and it's least toxic. So it's more opaque, but it's not going to cause the same type of reactions as number 1, high osmolality. Okay, so 6:2 ratio, dimer configuration. It has the structure and configuration of 2 joint ionic compounds, but reacts similar to that of a non-ionic compound. So osmolality in relation to our blood and tissues. So osmolality in radiographic contrast media is determined by the number of particles in a solution. It is written as milliosmoles per kilogram. In human blood, osmolality is 300 milliosmoles per kilogram, 300. Now if we introduce contrast in there, here was one that is ionic contrast, and remember the difference between ionic and non-ionic. Ionic is going to be more viscous, right? More thick. So in comparison to human blood, it's almost 3 to 6, 7 times greater in viscosity than that of human blood. So the shift to equilibrate is going to be very, very drastic. Whereas non-ionic is as low as 291, very similar to that of blood, and probably doubles, almost triples, but it's very similar to blood, and that's why there isn't such a sudden shift. Is that making sense? Okay. So therefore, with its blood, with its high osmolality, contrast could easily penetrate blood. This is going to be more problematic than non-ionic. But we also said that because we manipulate the molecules a little bit to make it less toxic, what else are we removing here?
Cations?
No, is it going to be as radiopaque as the ionic? It's going to be less radiopaque. It's less toxic, but it also means it's less radiopaque. So you're not going to get the same type of capacity that you would with an ionic contrast. So, bless you. So ionic, again, here's their molecular configuration. It's a 3:2 ratio. And a non-ionic is a 3:1 ratio. And I did an illustration here so you would understand that in a particular space, this 3:2 ratio, you have 3 ion atoms per molecule per 2 molecules. So you have 2 of them for a total of 6. And then here, you're only going to have 3 on 1 molecule. So which has more iodine?
The first one?
It's going to be this one, right? Because we've got a total of 6 versus only 3 over here. Okay. And then I just put over here when you do the average of the two, 3:2 ratio, 2 and 3 gives you a number of 1.5, and non-ionic is 1 to 3 gives you 3. It's been determined that with a higher N number, based on the number of particles in solution, is going to be the one that's going to give you more problems. So higher, more problems, lower osmolality is what we prefer. Okay, a higher numerical value, less toxic. All right, iodine concentrations of contrast will be determines the ability to absorb X-rays. So when you guys had a chance to look at your contrast media, not only will you see the brand name, but you'll also see a numerical value right after that, right? So here's an example. We got Omnipaque 240, IsoView 370, and Hexabricks 320. That number is telling you the amount of iodine that you have in that particular solution. So the higher the number, the more iodine is contained in that solution. So with that said, if this is 240, and let's just say I had another Omnipaque that was 320, which has more iodine?
320.
320, which is also going to be more thick and more viscous.
320.
320, all right? But why do we have different concentrations of iodine? Because it all depends on what you're trying to visualize. So if we're just looking at normal tissue, 320 would be appropriate in most cases. Just regular tissues and organs, okay? Now, if I were to use that 320 to image my basilar artery, okay, going to my brain, it's going to feel like somebody hit me with a sledgehammer, because it's so thick. You are taking up the same space that your blood vessels, which carries oxygen, and it's so thick and so viscous. The circulation up in the brain isn't as smooth, and that's what's going to contribute to your headaches. If I shot 340 down my femoral artery, it's going to feel like somebody just ripped off my leg. Okay? It'll give me the opacity that I need, but again, because it's so thick and viscous, I'm also minimizing the amount of circulation going down my leg. So it's not so much the contrast that you're going to use, but you also need to understand the iodine concentration and how it contributes in producing the image and the side effects of using a particular type of contrast. All right? So the higher the concentration, the greater the ability to absorb X-rays, and is said to be more radiopaque. Okay? Any questions? The viscosity of the contrast is a measure of the fluid to the flow, and it's determined by the number of particles in the solution and the attraction among these particles. Higher iodine concentrations tend to have higher viscosity, 300 over 240, so 300 is going to be more iodine, more viscous. The toxicity of the contrast on body tissues and organs is related to the chemical configuration. We were talking about it being ionic versus non-ionic, the osmolality, the iodine concentration, and lastly here, we haven't talked about this yet, is the rate of injection. it is said that if you inject contrast at a slower rate, it is more forgiving than injecting a large bolus of contrast media in a short period of time. In other words, if you inject a lot of contrast in a short period of time, there's a greater chance that you are going to experience an adverse reaction versus when it's injected slowly. Okay? The rate of injection. So why not use non-ionic? Huh? Well, if you were driving a car, okay, let's just say your car, why would you choose super unleaded over regular unleaded? Okay, it all comes down to economics, right? I'm going to buy super unleaded. It's going to be a little bit more expensive, right? It's going to be a little bit more expensive, but I know it's going to be better for my vehicle. But most of the time we can't afford super unleaded, so we go with unleaded, and it's cheaper, right? And it'll get us somewhere. So we're going to use the regular unleaded, even though we know that it may cause problems with our vehicle. Does that make sense?
Yeah.
Use a cheaper car. You're not going to get as far, but it's still cheaper, and it'll get you somewhere. So doctors will choose the cheaper one, okay, the cheaper one, than the more expensive one. Does that make sense? But here is the economics again. So if I get the more expensive non-ionic, I'm going to use the non-ionic because it's more forgiving to the body, it's less toxic. But what ends up happening is the doctor has to use more to get better visualization of whatever they're studying. So they end up using more anyway, right? And then you've got those who use the ionic. They say, well, it's cheaper, I get better visualization, but now there's a great chance of my patient experiencing some kind of allergic reaction. So they got to weigh, risk and benefits. What's better for them? But it all falls down to economics. Most places now have made the switches to non-ionic, but not all of them. So we're still using ionic forms of contrast agents. Okay, types of contrast media reactions. Anaphylaxis. What is anaphylaxis? It's an allergic reaction to an antigen that was previously encountered by the body's immune system. You guys remember my analogy about an allergic reaction? Because the key here is previously encountered by the body's immune system. You guys remember my analogy? Okay, here's the analogy, all right?
Oh, wait, that one.
Yeah, that one, yeah.
Okay.
Well, here's the analogy. So I'm going to take a huge vacation. I'm going to go to the Winter Olympics. Okay, Korea, Pyeongchang. Okay, I'm going to watch the Winter Olympics. And then meanwhile, I'm on social media. I'm telling people I'm going to be gone. I'm going to be gone for 2 weeks, right? So I pack up my bags and leave. In the meanwhile, was it dumb for me to tell people I was going on a trip and I'll be gone for 2 weeks?
Yeah.
Yes, that was stupid, okay? Because now they know I'm going to be out of my house. So, get these people come in my house and they take all my belongings, right? And that was stupid. So, they eat my food, they sit down on my chair, they're lounging around on my couch, they're playing on my PlayStation, they're sleeping on my bed, and then they take whatever they can with them and pack it in their van, right?
Bastards.
Okay? Yeah, and nothing was done about it. There was nothing I can do about it. So I come back and I found my place ransacked. But nothing was done. So now the next time that I leave, first of all, I'm not going to go on social media to tell people where I'm leaving, but I'm also going to now have my house ready for the next time it happens. Okay? So now I've got my barbed wire. Okay? I've got my Rottweilers, got my heavy security system. So next time that they arrive, if they decide to arrive at my house again, I'm better prepared. That's basically how an allergic reaction is. Nothing happens the first time. Okay? It's the second time that you come around that you are prepared for it. Your body recognizes it as a foreign substance, and now it's going to do its best to get rid of it. okay? But in doing so, okay, but in doing so, your body is going through some certain types of changes which aren't positive to get rid of that antigen. That is what an allergic reaction is.